So what is neuromorphic computing? So neuromorphic computing, the word was coined by a very famous professor from Caltech named Professor Fabrication. And basically it means designing systems whose principles replicate that of the human brain. So why is that? Why do we want to design the human brain? And unfortunately, you can talk to biologists. So there's a large amount of research happening in biology, in electronics, and computer science, trying to figure out how the brain works. The brain is still a mystery to us. We've understood a lot in terms of the chemistry, in terms of the organization, but we still don't understand what makes us think. How do we think, right? And then to put things in perspective, let's think about, since all of us here are electrical engineers, let's think about, suppose I have to compare a computer to a brain, right? What is the difference in the two? And why do we want to replicate the brain? So you can think of grossly a few differences between the brain and the computer. First thing is, most of the processing in the brain is a parallel processing. Whereas in a computer, we normally do a serial processing. One after the other, pipelines where you have serial processing. We have a movement towards parallel code processing. Still, most of the processing is essentially serial. The big difference here is right there. If you think about any complicated computing jobs that you want to do on a silicon computer, you need to spend substantial amount of power on it. Right? So if you think about the backup, so all of you use the cloud, right? The Amazon cloud, Google cloud. Where is the cloud? Where are all the operations of the cloud happening? They're happening in the server rooms, which are made up of these large AC cooled rooms where there are continuously large circuits, large servers running continuously, right? And you need active cooling to ensure that the transistors are running at room temperature. All of you by now know that if you want to extract a lot of performance from the transistors, you don't want them to heat up. Heating up chips is bad because it ends up to essentially damage, low lifetime, etc. Whereas the brain does all this with the food we eat. If you think about the estimate of the power in the brain, it's roughly 50 watts. The other big difference between computers and brain is that the computers, it's digital, ones and zeros. Right? We code up the world around us in ones and zeros, and then we process those ones and zeros to make sense to estimate the next steps. And it's a discrete time process. In that, we are sampling what is happening around us and then making decisions based on the sampling. Whereas the brain is a very different way of doing things. It's all happening in analog. We don't design zeros and ones. We design the bits. Think about your body. You can sense temperature, whether it's very cold, slightly cold, not cold, etc. Right? So point is that it's more analog and it is a continuous time. So you can react instantaneously to any change happening. The other big thing in the brain versus the computer. In the computer, we think about a memory and a CPU. Right? There is a special allocated space where things are stored, and then there's a special allocated space which is doing all the logical operations, which is controlling how information flows, how information processed, etc. Whereas in the brain, what ends up happening is when you stick probes into your brain and you start to analyze, okay, how are the electrical signals moving in the brain? You tend to see that suppose a person is viewing, suppose I'm looking at something, I'm scared of it. When you look at the electrical signals that light up in the brain, it's not restricted to a particular area. There are few areas which light up. At the same time, if I eat something, right, which I like, so there's a pleasure sensor in the brain which gets kicked off. It so happens that these areas are not isolated. In a sense, I cannot say this part of my brain is the pleasure sensor, this part is the visual cortex, etc. Right? When I'm sensing, when I'm making sense of what's around me, different areas of the brain light up, which tells you that the processing is not isolated, rather it's very distributed across the entire system. So that's something completely different from what a computer does. The big thing in the brain is as we grow, we learn. As we learn, so the brain is continuously looking at the environment, making sense of it, processing, learning. So the big thing which we want to emulate, and this is what artificial intelligence is about, is that you want to design a system which evolves with time. As and when you give it more data, as and when you give it more, what do you say, decisions, it evolves with time. And finally, you want it to be robust to errors. Right? If there is an error in processing, it should be able to reassess and recalibrate itself. Right? So that's the difference between brain and computer. Right? So essentially, what you want to do is there is a school of thought that says that probably we want to move to a brain kind of processing which will enable us to do lower power and probably smarter ways of designing systems. So let's think about the basic unit of the nervous system of the brain. It's essentially a neuron. And I'm not going to go too much in details of biology, but just to give you some numbers, we have approximately 1E11 neurons in the brain. Right? The big difference is that we have approximately 10,000 connections between each neuron. So if you think about a transistor, we don't have that kind of fan-out. Fan-outs in digital technology is roughly 10. In CMOS, you can go up to 15, right? So, but that's the fan-out limitation. That is the output of one transistor can maximum drive around 10 to 15 transistors. Whereas here, you can have connections which are way more than what you can achieve in silicon. So if you think about the neuron, this is the body, cell body, and then you have what is known as an axon and a synapse. A neuron has what are known as dendrites here, right? So what you have is that these dendrites connect to adjacent neurons, and information flows along the axon to the adjacent neuron. Right? And this is the cell body. And an important piece in this puzzle is known as a synapse, which is nothing but the interconnection between adjacent neurons. So how do neurons communicate? So let's think about a simple neuron. Either here. So ideally, the input system, it has multiple inputs, right? And the way the output is generated in neuron is that the output is not generated as a linear sum of this. What happens is that the output is generated as a pulse. For example, suppose I touch something hot with a finger. And touching something hot with a finger, if the temperature is not high enough, I don't mind touching it. But beyond a certain temperature, there is an action which says pull your finger back. So what is happening here is that there is something known as pain, right? And what is pain? Pain, there is a certain threshold. So as your inputs come in, the signal to pull your finger back doesn't happen until it reaches a certain threshold. So an important part of communication neurons is what is known as a threshold. Right? As it gets signals, right, from various sources, a sort of integration happens in the cell body, and then once it reaches beyond a certain threshold or an action potential is generated. Right? So the neuron sends information or sends a signal to the next stage only after it is activated, and that activated has a certain threshold. Okay, sorry. An important aspect about replicating neurons in system is known as a timing dependent plasticity. So remember, in neurons, all communication is happening through pulses. Right? There is no level based. It's not like a voltage level of 0 or 1 or some finite value. That is a pulse. Now, if you've done systems, so you know something known as causal and acausal systems, right? So, how does a neuron identify whether an action is causing a reaction or not? So, that is based on something known as a spike timing plasticity, or what we do essentially is we look at so you always have a pre-neuron and a post-neuron, right? And if the post-neuron fires after the pre-neuron, we judge that the system is causal. Whereas if the post-neuron has fired before the pre-neuron, then we say that this particular neuron in output is not important for this output, right? So by identifying the timing between the firing of the pre and the post neuron, I can talk about causality. That is to identify which are all the inputs that are important for a certain output function. Right? So this will come important when we start thinking about how to design the system. So what's important is the relative timing between the pre and the post. The relative timing between the two will tell us whether it is causal or incausal. And what happens is we also use this phenomenon to decide which is a important signal or which is not an important. So when you're learning, so why is this important? Suppose you're designing a system which is learning, right? So you give it data, it is responding, right? And as it gets data and responds, you start to build a network as to how are the inputs talking to the outputs. And that's when essentially we use this STDP to determine what are all the connections between the various neurons. So, what is synaptic plasticity? It is the relationship between the output and the input neuron. Right? So, ideally, what we want is so remember, now we're talking about analog domain. It's not like I have three inputs, have an output. The output is a Boolean function with three inputs. Rather, I have something known as which is the most important output, which is the input, which is the second most important input. Right? So we're talking about importance. In addition to it being a causal factor, there is also an importance factor. And that importance factor is essentially known as the synaptic weight. Right? So what that is telling you is, if suppose I have a large weight between a certain input and a certain output, that tells me that that input is the most important input to fire the particular output, right? So these weights are kind of like an importance matrix, if you will. So it tells you how, among all the inputs, which is the one which is the most important. And the way we train a system is we essentially want to identify these weights. So identifying these weights is essentially training the system. So when you're training a system, these weights are going to fluctuate up and down depending on the outputs. And the change in synaptic weight is essentially going to tell you the relative importance of the various inputs at the stages. And it's a very good paper here to read if you're interested. And I took this quote from that paper, which says that cells that fire together wire together. So when two neurons are causal, you'll see that they will have a very high weight between them. If I'm designing the neural system, I will ensure that they have a large synaptic weight between that input. So why are we looking at all this now? So as I told you, this field has been around since the 1980s. People have been working on neural networks, trying to replicate neural networks on silicon, etc. So that this work has been going on for the last 30 years. Why the interest now? That's primarily driven by the fact that we are now dealing in an era where data is very prominent. So there's a lot of data available to us. And why is that data available? Because memory has become cheap, transistors have become cheap. So because of the fact that we've had these huge changes in computing, we have access to a lot of data. And when you have access to a lot of data, you saw the rise of machine learning. What is machine learning? Nothing but using that data to design systems which are particularly suited for a special class of data. And so when you have all this data, you want to design systems which are specific to that kind of data, that kind of application. We are also seeing a slowdown in clock speed. Right? All of you probably thought about this, Moore's law. As technology has gone over the last 20 years, you've seen the rise in the cost per technology. So if you're going to make a transistor technology in the 2 nanometer node, it's going to be almost 4 times the price of 5 nanometer node. So the cost of the transistor is not, and think about it previously. Previously, when not scaling led to, the reason we scale transistors because it gave us cheaper chips. Right? Here, what you're seeing now is a huge investment cost every time we want to move to a new technology, and the return is not that high. So what you're seeing is essentially that transistor speed is not improving. But we need a large amount of computing power, because especially when you start dealing with a lot of data, we need to design systems which are able to process that data, identify networks. So which means that in addition to technology, we need algorithm innovations. So we need to think of a different way. And that's the reason why you see this increased number of papers in neuromorphic computing, etc., over the last 10, 15 years. And the reason is primarily because the way we think about designing architecture today is not enough. We need to think of faster, cheaper ways to do that for artificial intelligence applications. So here's some slides, some figures I pulled out from the recent publication. And plotted here is showing the compute performance as a function of years. And you see all of a sudden with the rise in the data science here, so this you see two slopes, if you will, right? And what you're seeing here is these are from the old neural architectures, and then with the rise of embedded memory and faster technology, you see a very different growth. So this is because of the rise of machine learning that you see now there is a huge improvement in performance that you're seeing over the last few years. But also what you see here is the cost for per operation as a function of time. As you're dealing with a lot of data, you end up creating systems which require a lot of transistors, which require a lot of computation, which means that the cost of doing these machine learning jobs is increasing. So this is a big problem, right? While we have a huge market for these kind of applications, the cost is very high. You need to figure out a way to design systems that are cheaper and energy efficient so that you can deliver. And then I just wanted to throw some numbers as to what are all the fields we're looking at, right? So there is this whole analytics, which is largely CPU driven, but then you have the whole AI part of applications, which is cognitive AI, machine learning, and deep learning. And what you're seeing is there's an explosion in this field, which is deep learning, primarily driven where you have different customers. Even today, if you look at the startup field in semiconductors, there's a lot of startups in this area. Right? So almost, I know for around 15, 20 startups in this field who are working on developing efficient hardware, and everybody's racing towards the first person to build an ASIC. So this is where there is a lot of demand for energy efficiency, because this is going to be in the ASIC field. So it's not going to be a generic server or a GPU, rather it is going to be an ASIC, and the ASIC is needed because that's going to reduce your cost. If you're going to do everything on GPUs or FPGAs, it ends up being a very expensive proposition. And so the question is, how do we put this technology on standard CMOS technology in an ASIC at low cost to get the maximum benefit? Okay, so how do you think about a neural network when you think about implementing it in silicon? So as I told you, a neuron takes bunch of inputs, integrates it, if you will. Once it crosses a certain threshold, it gives out an output. So the way we thought about um, implementing that in a circuit or in a system would be, and this is where machine learning is used. I mean, this is the foundation of machine learning, and we use similar things when you're building circuits. Is you think about a neuron. A neuron can be implemented as a, suppose it had multiple inputs, say x1, x2, etc. Right? Each of them, as I told you, is assigned a certain weight. Right? The weight kind of tells you the importance of these inputs. And what we want this neuron to do is we want this neuron to sum up. So it's kind of integrating the weight with the input. So it's creating a sum. And then once it reaches a certain threshold, I want the output to 5. Right? So you have what is known as a linear sum of Wxi, Wixi. And that is backed up with a nonlinear function. Then this nonlinear function is essentially going to be a function which is going to kick in a pulse the minute a certain threshold is reached. Right? So this is how you want to implement a circuit. If you think about the circuit you want to implement, it would be something like this. It would be a circuit which implements a linear combination of W times X and then applies a nonlinear function to it. And so as I said, we scale the input with its weight. And the brain is believed to learn through these ways. The way we think about, again, this is not a proven way by which the brain works, but this is the way we have modeled the brain to replicate it. Right? It's hard. So we know that if you, there's a lot of work done in biology where they measure the action potentials of the nerves, as especially in the very seminal work which got a Nobel Prize, where they measured the action potential along a single axon of a frog, and you actually see the action potential travel across. So we do know pulses occur in the nervous system, and we do know some sort of an integration happens, but this is the simple way by which we as engineers have decided to implement this system. And learning, what does learning mean in this technology? Learning essentially means is the job when you throw the system in the field and ask it to learn is that the system has to identify what are all the different weights for the various inputs that are present. So that's the meaning. When I say the system has to learn, that essentially means that the system has to identify what are all the weights that are present in the system. And this also tells you that suppose, so this is where the reconfigurability, if you will come, is that based on the environment you're throwing the chip at, different chips in different environments or different chips with different data sets will end up with different weights. So every time, so in an ideal world, you want to design a chip where there is a continuous amount of learning and inference happening. Right? So if you think about neuromorphic technology, there's always learning and then implementation. Talk about that. So if you think about a neural network, again, most of you have done any sort of neural networks or machine learning are familiar with this. We have an input layer, we have an output layer, and we have a middle layer. So what are these? These are essentially neurons. Right? And what we're trying to build is, we're trying to build this network and assign weights to each and every connection between this neuron and the subsequent neuron. So by defining inputs and outputs, as we send inputs through and measure outputs, we let the system settle to what is the weight in every part. And once that system is learned, then we can use that system in a live field. So if you think about the ways a neural network is made up of, first thing you see is there are a lot of connections. So you have to design a 2D system which has a lot of contacts. Second thing you see is that these connections are essentially the synapses. So you have a neuron, and synapses in between. And the synapses are nothing but the weights in our system. So for example, suppose you're designing a system to an image classification system. So essentially your pixels are going to come in at the input layer, and your output might be a letter or a number. So you're identifying letters. So your output can be one of the 26 letters of the alphabet. And so essentially your output neuron is going to be Now that you can code it as a digital signal or as an analog signal. So that's going to be your output. Your input is going to be all the pixels that's present, and then you have to design this network which is going to essentially identify the weights in the weight system. So anytime we talk, so what's deep learning, right? Anytime we talk about, suppose we have multiple hidden layers. So what you see is an input layer and output layer. This layer, this blue layer inside, is a hidden layer in the sense that the input has no access to it, the output has no access to it. What's happening internally, and that's something where the weights are going to be assigned as the information flows through the system. And you can think about, so here's a simple system where you have a single hidden layer. Now, as you add more hidden layers, the system becomes essentially more convoluted, and therefore you can go to larger spaces. So if you think about a vector space, you can hit more of the span of the vector space if you're dealing with more hidden neurons. But the drawback with that essentially is that the learning gets complicated. But again, algorithm stays the same. But typically, if you look at most publications today in this field, most of them deal with a maximum of 2 to 3 hidden layers. Nobody goes more than that. I don't know how much you guys are following machine learning. There is a lot of ethical issues associated with machine learning too. Primarily dealing with many times when these systems run, it's hard to backtrack. Why did a system decide a certain thing? So now what's actually being recommended by some of the leaders in the field is that not to have more hidden neurons, because back traceability is an important aspect of design of systems. That is, at any point of time, you need to have a record as to why a certain decision was made by a system. So which means that every time a system outputs something, you should be able to trace back exactly why it did that output. And so having more than a couple of hidden neurons becomes very hard to backtrack that system. Therefore, generally we see that in most commercial applications, you see not more than 2 hidden layers. So, I talked about 2 words, inference and training. So what's training? Training is nothing but determining the weights in the neural network. So when I'm throw the neural network in the field and ask it to learn, that is what essentially training is. When you run the program with the weights that is learned, it is known as inference. So when it's doing its processing based on the data you've trained it at, it's known as inference. And during weight update, that is when you're doing the training, is when the weights are updated. So there are multiple algorithms available for weight update. The most important one is the backpropagation. If you look at most commercial hardware in machine learning, most of it implements the backpropagation algorithm. So how do we train weights? So there are different ways of training the system. The first one is known as super. So what is training? So suppose, let's take an example, right? Again, let's go to the classification that you have a visual system and you want to, one of the common examples cited in most papers is identifying numerals, right, from 0 to 9. Suppose I write the 0 to 9, I want to identify what is it, a 0 or 1, 2, 3, 4 to 9, right? So in that case, different people have different ways of writing numerals, right? And so you can think about the field as a bunch of pixels and you can code them as 0 or 1. So suppose I have a 4 cross 4 array or a 10 cross 10 array, whatever you have. Now, there are different ways of learning. So suppose I write a 0 this, or I can write a 0 with a hash through it, right? Or I can draw 0 as a perfect circle. I can draw 0 as an oval, right? There are different ways of drawing a 0. But what do you want? You want all these to be identified as a 0. Right? So the first method is known as supervised learning, where essentially what you do is, before you release the system, you define, okay, these are all the inputs, different ways of writing zeros, and all of them are mapped to the digit 0. Similarly, if I think about 1, I can write a 1 like this, I can write a 1 with an arrow, I can write a 1 with a line below, etc. So I will try and give as many of these options available, and every time I give this option, right? I will map it to 1. So what the supervised learning is, for every input, I am labeling that input and classifying it. So I'm going to say that when I'm training, so remember, training is just a bunch of input and a bunch of output, right? So when I'm training it, I'm going to say, okay, these are all the different ways of writing a 0, and all of them are mapped to 0. So when you run it through the neural network, right, you exactly know what the output is. So then the weights get updated based on that output, right? So that is known as supervised learning. So here you have a bunch of input, you have a bunch of output. The input-output relationship is clearly marked. It's labeled, and so this is the easiest way of doing learning. It's the most predictive, and it is the least power hungry. The drawback with the system, however, is that you need to label and classify, right? Which means that a priori you need to know what are all the different ways of writing a 0, and they all have to be mapped to 0. The other way is unsupervised, where it's not mapped. Like obviously you can't do something like that to the numbers, but the way to do it is the samples are not labeled. So you continuously keep running the system using HTTP and identify what is the first of the data. Right? So I can write 0, send it on, and have some sort of a weight system assigned to it, and then update. We also have combinations of these, right? One is known as semi-supervised, where it's a combination of these two, where it's not completely supervised. Some data is labeled, and then we use that to do a labeling of clusters. So it's a combination of the two. We also have what is known as reinforced learning, which is a derivative of the unsupervised, where essentially you give a certain reward if the network has done well, or you give a certain penalty if the network is wrong. So that enforces it to push a certain way. And the easiest method is fine tuning. For example, suppose I already have a network which is trained, then if I send it into a new environment, the update in weights is preferably less. For example, suppose I used supervised learning and updated network, I can now send it into the field and then use very simple algorithms to fine tune it around that center point. So that makes it very, very easy. It's very fast and it's most efficient. So here's what we are trying to do, right? So if you think about traditional computers, this is what the traditional computer looks like. This is the one human architecture, where essentially you have a CPU, you have a memory, you have input, you have results. Every time data comes in, the CPU accesses data from the memory, processes it, sends data back to the memory, then sends the results out. So what happens is, if you think about today's processors, right, a huge amount of cache, right? So you have this big bus, the memory to CPU bus, which is going to carry a lot of data, and this bandwidth of this bus is limited. So the speed of the system, even if you make the CPU very fast, if you make the access time of the memory is very fast, speed of the system is going to be determined by what is the bandwidth of this bus. On the other hand, the way neural networks works is that I push the processing into the memory. So I use it. So what I'm doing is I'm not relying on this bus, rather I'm pushing some of the logarithmic arithmetic functions into the memory. So you have something like this, where the memory has processing coupled onto the memory, and then you have a CPU. This way what happens is that this bus is no longer the limiting factor in your system performance, and so you end up getting more parallel processing, and hence you get better output. So this is how a neuromorphic system works, and this is the traditional transistor, traditional one-human architecture. And so what you essentially see is you want to build logic into memory. So no longer is memory just associated with dealing with zeros and ones or storing data. You want the memory to be able to process data too. So that's one of the key differences between the neuromorphic system and the traditional CPU-based one-human architecture. So, as some of you would have read, crossbars are the baby when you architectures. Right? And what is crossbar? So if you about this linear function, f is equal to summation of wx. Now, w times x. Now, if I think about y as a current, x as a voltage. Remember, x is an input, right? It's a signal input. Y is a signal output, so it has to have currents and voltages. So if you think about x as an input and voltage, y as an input and current, they can talk about the weight as a conductance, and then I can essentially implement I as sigma g times b, right? Which is nothing but Ohm's law. B I is equal to B by R, or I is equal to G into B. Right? So by implementing, so I can implement a summation. So this is known as a multiply and summation, right? You multiply these products W1 X1 plus W2 X2. That can be implemented as G1 B1 plus G2 B2, etc. So you're converting this problem of multiply and accumulate into implementing Kirchhoff's law in a resistive network. And so that's essentially the origin of the crossbar. So what you have now is you have weights associated with resistors in the system, and you have different inputs across the word lines. Right? And so as this input comes in, the conductance of this determines the current that flows through this column. Right? And so the column currents are essentially nothing but the summation of the individual products, right? Because this current here through this branch is going to be V times G. Similarly, V times G. And all of them are flowing through the same node. So this current that is flowing through the column is essentially going to be a summation of GB, or the sum of the linear products. Now, what we therefore want is, we want a method by which I can predictably change the resistance of this resistor. Right? And this is the weight, right? G is the weight. And that's essentially why we use non-volatile memory devices, because non-volatile memory devices will be the ways by which we can implement these resistors whose resistance can be changed, and that is where the weight of the neural network is going to lie. So there are different ways of implementing neuromorphic systems. So the first way to do is, obviously neurons, as I said, are a bunch of inputs, then the synapses are essentially local memories that are interconnected. So there are two ways to design. One is the digital way, when a neural network, neuron values are encoded in zeros and ones, and then you send it through the GPU FPGA. So this is what, if you look at Google's Tensor product, if you look at NVIDIA's GPU product, right? This is the way they're implementing it. Basically, because of the fact they have access to massive SRAMs and GPUs, they're essentially converting this problem to an arithmetic problem. And by accessing a large amount of compute power on their chips, they're able to implement the neural network simply by implementing multiplication and addition. So that's the brute force method. You need a lot of silicon and you need a lot of power to do. What researchers and some of the startups believe is that in addition to this, we also look at spiking neural networks. So this is closer to how the brain or the whole body works. And we try to see if, instead of coding the neuron in digital, right, actual numbers, we code it in terms of spikes, right? And then use those spikes for processing, and that should be able to give us a system which is more energy efficient and which probably is smaller than this system. Now, if you talk about predictability, obviously this is going to be a better system because it's implementing actual multiplication, actual addition. But you have to always ask the question, is that needed? Do you need accurate numbers, or are approximate values enough? So a big part of neuromorphic computing is that it's redundant, it's error redundant. So it's not necessarily I need to have floating point values up to the fourth decimal or fifth decimal. I can make a decision with the whole number value. So that's the difference between the way we think about a regular DSP architecture and a neuromorphic architecture. So here are some of the implementations. Again, this is a great paper to look at. It's a great review paper. So these are some of the implementations that people have published using either level-based or using spike systems. Again, you just see spike systems are the closer ones to the brain, but they're harder to implement. This is where it's easier to implement, and so you see a lot more papers in this than in this. Okay, so far we've discussed all these architecture. Now I want to understand why is memory important. What is this about? What is about memory that makes it so attractive to us? So first thing is memory elements like resistive RAMs. We'll talk about that in a bit. There are these special resistive RAMs which have a very elegant and easy method of updating resistors. And this, in addition to the fact that they are a much smaller area. So if you want to implement an adder, right, it's going to take a large amount of area on the chip. Rather, if you implement that using a non-volatile memory, you'll see that the area is substantially less. The other big thing that the non-volatile memory gives is what is known as a multi-bit storage, and we look at how that helps. And that is another reason why non-volatile is a generic good. So it's the same amount of area in silicon. So if you think about today's NAND flash, right? Buy any of your memories, USB stick memories. You see that every flash cell doesn't only store 0 and 1. If you look at the latest Intel product, it goes up to 5 bits. So one flash cell can store up to 5 bits of memory. Right? And so you see that non-volatile memory in the same area, you can stuff a lot more memory than you could do in previous generations. And the other big thing with non-volatile memory, which doesn't happen in SRAM, is that non-volatile memory can be powered off with no loss of data. So you don't have to keep the system on at all times and wait for leakage, right? Once it's trained, once it's not in use, you can shut off the system. The weights remain as is. And then when you turn on the system again, it's back to operation. Right? So that's another advantage with non-volatile memories here, which SRAM will have. And so one thing which I want to highlight here is that, again, you see that this has happened in the last 10, 15 years, right? And the reason being because Flash has undergone tremendous changes from what it was 20 years ago to what it is today. Right? So there are a lot of memory options available, and some of these memory options have actually they found a new birth in optics. They died in storage class memory, and they've actually found advantage here because of their small size. So what are the properties of an ideal memory element you want to use here? First and foremost thing is the dimension. Right? Remember, we are putting this in logic, right? We want to put it on top of logic. So we don't want a memory cell which is way bigger than the logic. So ideally, you want the dimension of the memory to be of the order of the transistor, logic transistor. And we'll also talk towards the second half of this talk as to how 3D integration has opened avenues to actually do this all in one chip. Second thing is, as I told you, we believe in analog computation, right? So we want that memory to store any weight. For example, suppose I have a weight, range of 0 to 5, say. My memory should be able to hit any value between 0 and 5. I don't want it to hit only 0, 1, 2, 3. So what happens is, by the ability of having multi-level states allows us this analog-like behavior. Unfortunately, what happens, we'll see is that because of the variation present in memory, it's not possible to get an ideal analog-like behavior. If you're working with one device, that would be perfect, but you have to work with an array. But you'll end up seeing an analog-like behavior. So you have a lot more states. The third thing is this dynamic range. When you think about weights, right, you want the weight range to be as wide as possible. That will allow you to ensure that you can take a lot more inputs and then assign weights accordingly, right? So if you have a weight system of say 0 and 1, let me give a worst case example. Suppose my weight can only be 0 or 1, then essentially I've designed a digital system. So either the input is required or the input is not required. But once you have a weight which can go say 0, 1, 2, 3, 4, then I essentially have a 4 level of gradation in importance. I'm able to go 0 to 10, I have a 10 level gradation of importance, right? So having more range in the weights allows us to have a better system. It will allow you to come to a system which is less error prone. We also want the weight update to be as linear as possible. And we talk about that as we go through. Another big part, if you think about older non-volatile memory, say if you look at papers in the 80s and 90s, when we were doing chisel flash and EEPROM, you essentially see that it took a lot of energy to program. Right? If you think about programming a non-volatile memory, it's normally associated with tunneling electrons into the floating gate and tunneling electrons out of the floating gate, which required a lot of voltage, current, and so the power was very high. The advantage with some of the embedded memory elements that we talk about is that they have a very low energy consumption. So programming is relatively low power as compared to the old non-volatile memory. Finally, we also want retention and endurance. What does endurance mean? Endurance means that suppose I store a state, I want that state to remain forever. I don't want it to change. I don't want it to decay. And the last thing is uniformity, right? And this is a big problem today. If you look at one of the fundamental drawbacks of in non-volatile memory-based implementations, it's essentially it's very hard. Technologists are finding it very hard to design memory systems which have as low variability as possible. The problem is variability is a problem today even in logic. Right? So if you think about any of the technologies, 18A technology, 20 technology, 3 nanometer technology, almost all of them are limited by the variability of transistors. So the variability continues to be a problem. Variability is going to become a worse problem as technology scales. So we need to find a way to deal with it. So today we are limited by the variability. So this roughly just puts the numbers out for you. Device dimension around 10 nanometers, multi-level states, ideally up to 100, so it becomes analog. Energy consumption of roughly 10 pepejoules. Dynamic range around the same, and retention endurance. So we'll talk. I want to take a break now at 10:30. 10:30. We have finished the section. All right. So we'll talk about two leading candidates which have been used in almost all implementations in literature. One is the phase change memory, spearheaded by IBM, and the resistive memory device, which is being done by almost everybody else. All right, so so this is some again very nice data compiled from Stanford, which shows the trends in memory over the years. So these is for a storage class memory. I just wanted to highlight that some of the RAMs that we're discussing, the RAM, the CD-RAM, the PCM, all of them initially started off as candidates for storage class memory. What is storage class memory? Storage class memory is the memory we use in USB drives, the memory we use in your solid state flash drive, right? So that's storage class memory. And what you end up seeing is they have exhibited pretty high capacities. Right? And the problem with these memories has been with endurance and retention. Right? So therefore they've not made it into storage classes again. And the other advantage is NAND. Once it moved from 2D NAND to 3D NAND, all of a sudden saw a huge rise in the number of bits available per unit silicon. And so therefore I think it's become very hard to beat NAND as of now. So let's talk a little bit about phase change memory devices. So phase change memory devices are made up of what is known as an GST. What is a GST? It's germanium antimony telluride. The property of this material is such that the resistance of the material depends on the crystallinity of the material. For example, suppose the material is amorphous, it shows a high resistance, and when the material is polycrystalline, it shows a low resistance. So there is an ability to modulate the resistance of this material by changing the crystallinity. That's where it started. Now the advantage or the second property of this material is that it melts easily. So remember, how do we draw, how do we create silicon lattice? We take the silicon melt and use the crystal and pull it out, right? And that's how we create the silicon crystal. So the same thing happens is the way it works here is you have this material and you have a heater. A heater is nothing but just a resistor with a large current flowing. Depending on how much current you're flowing through it, right? You can either heat up this to a larger temperature or lower temperature. And depending on the cool down, right? So this thing melts around 600. So depending on whether you cool it down fast or you cool it down slowly, it either becomes amorphous or crystalline. So, and therefore it changes the resistance. So if you think about it, this heater element, right, is going to melt. So essentially, initially say it was crystalline. When you heat the material, it's going to melt the material around the heater. And then how do we control the heating? We control the heating by applying a current at this point. Right? So this current can either be a short pulse, short tall pulse, or a long, a tall short pulse or a short long pulse. Right? And so what happens is that if you apply a very high current for a short time, temperature is going to rise up very quickly and it's going to cool down instantly. And so what ends up happening is ends up amorphizing. However, if you have apply a current for a longer time, right, it melts, and then since you're giving it a slow time for it to cool down, it is going to get into crystalline state. So by applying the right pulse, you can either convert the material into low resistance or a high resistance phase. So this is the TM of the image, and you clearly see two phases, the crystalline phase and the amorphous phase in the material. So by changing the amount or the ratio of the amorphous to the crystalline, I can change the resistance of this material. Right? So if it was fully amorphous, I'd have a resistance. If it's fully crystalline, I'd have a resistance. And when playing around with the ratio of these two, I can change the resistance. Right? So I can get any resistance I want by changing the ratio. How do I change that ratio? Applying the right pulses to the heater element. So here is some data. Again, a lot of this work is similarly done from IBM. So you see that here is a programming current, this is the resistance. So you see that you can pretty much, by changing the programming current, you can pretty much get a large, so it goes from roughly 2e10 power 4 to around 1e7. Right? So you're able to get a large change in resistance by playing around with the amount of amorphous to crystalline material. And similarly, you can also go from crystalline to amorphous to crystalline by applying set currents. Right? So this is known as the reset current, this is a set current. What you see is that the conductance, if I plot a number of pulses, you see that the conductance, so here is the problem. As we look at multiple devices, as we look at the same device done multiple times, you see there's a variation. So when you're designing a circuit, you need to be aware of what this variation is and you have to design for it. Another nice data is the various conductances as a function of time show not that bad relative to resistance. Right? But again, as you see, as you go to high resistance, you see this drift. So that has to be accounted for when you are designing the circuit of this device. So as I said, the big problem with this device is that resistance drifts with time. And therefore it becomes very, so suppose I had two states around this resistance, one state can morph into another state. So therefore this limits the number of states you can actually have in a phase change memory device. Obviously you can add additional circuitry and detect this, but that requires more area and more cost. And here's a slide on the endurance. That is, every time you cycle it back and forth, right? So every time you write the high state, bring it down, write the high state, bring it down. You see that around 10 power 9 cycles or so, the resistance numbers are pretty good. This is from Samsung. Again, this is a little bit old data. This is sort of 2008, and this was done when Samsung was looking at this as a storage class memory. So therefore, it required high endurance levels for storage class. Of late, the numbers have, I mean, for our applications, you don't really need that large an endurance, but good to know that it can achieve that. So let's talk about the other kind of device, which is the resistive memory device. So resistive devices are of two types: filamentary mechanism and an interface dominated device. What happens with filamentary mechanism? So this came about when people were working on high-k dielectrics for logic transistors. What turned out is something which we think about random, right? When you apply a large field to an oxide, what happens? There's a current. Now, what we saw in transition metal oxides was that we create what are known as conductive filaments in the dielectric. And essentially, when you create that filament, all of a sudden the dielectric behaves like a resistor. Because now you have a resistive path between the two electrodes. And so we see very specific oxides. The leading candidates used to be dioxide, hafnium dioxide, tantalum oxide. You see, so this is a chart showing bunch of metal oxides which have these switching techniques, but the key ones which have found use and we see later in RFs are essentially dioxide, hafnium oxide, and tantalum oxide. And what you see with them is, we'll take a look at how it works, is essentially that by creating these conductive filaments, I can play around with the resistance of that filament. So, how does an RM work? The RM is essentially consists of an insulator layer stuck between two conductors. We have something known as a forming pulse. That is when you apply very high voltage across these two and you initiate breakdown. So if you think about the same logic for a logic transistor, right? This is a bad thing in logic transistor. You don't want, this is the gate dioxide, right? Hafnium dioxide is in the gate. You don't want that gate to break down because you want the gate to be a capacitor. However, when you apply a large voltage, right? Fact being that there are a lot of oxygen vacancies present in this hafnium dioxide matrix, they tend to create filaments. Now this is one filament, it's a very random process. Different filaments are created. And some filaments become that long that essentially short the two conductors. So what happens in that case all of a sudden now is you have a low resistance between the two conductors. And by playing around with this filament thickness or filament length, you can essentially change the state of the memory. Right? So in the worst case you have a short, so this is going to be a low resistance phase, this is going to be a high resistance. Right? And when I mean resistance is the resistance between the two conductors. These are your two electrodes, and if I measure the resistance between these two electrodes, if a filament is present, it's going to show a low resistance. If the filament is not present, it's going to show a high resistance. And you control this filamentary mechanism by applying a certain voltage. And so what you end up seeing therefore is that you are able to change the resistance of this film dynamically. And that's the operation of the RM. So there are two modes of operation: unipolar, where everything happens only in one direction, and a bipolar. So let me walk you through. Initially, we are in the high resistance phase. This is the blue phase, right? And when I reverse, so when I apply a negative voltage, right, beyond a certain point, so this point is known as the reset voltage. Beyond a certain point, I create a filament in the device. Once I create a filament in the device, the resistance drops here. And then the device follows this low resistance curve here. Now this low resistance curve it follows till it hits another voltage here, at which point the resistance filament breaks and it goes back to the high resistance. Right? So if you think about it, so you don't want to operate around these voltages. So these are the voltages by which you change from high res to low res. But in that region, if you operate around the voltage, you will get the right resistance. So this is the mechanism. This is known as hysteresis. Right? Anytime you have energy saved here, that is known as hysteresis. The same thing can happen also in the unipolar side, where essentially when you go to a high enough set voltage, and then when you're in that state, when you come down, you get the reset. So again, unipolar and bipolar. We mostly talk about bipolar devices because they're easier to implement and make fast with. So here's some measured data from a bipolar device, and so you kind of see the two resistance states. Now what happens is you'll see later that it's not, so this is the resistance, if you will. The slope of this curve and the slope of this curve are the resistances that are going to create your weight. What we'll see is that you not only hit these two resistances, by playing around the set voltages, you can hit any resistance between these. So what you end up seeing is different curves with different resistances. And that's the property of the RAM, which makes it very, very attractive for implementing in the crossbar. So there is amount of variability. So here is again, this is from another paper showing you the different set and reset. So again, what is forming? The forming is very critical. So essentially, if I take hafnium dioxide and switch it, put it between titanium and nitride on both sides, and if I measure, I'm not going to get a current. Hafnium dioxide, annealed is going to be a pretty good capacitor. What happens is if I send it through a foaming process, that is when I send it through a high voltage which causes the filament operation. Once that is done, once I've created a stress-induced leakage path, then it operates as a RF device, right? So to operate the MIM capacitor, the hafnium dioxide with titanium is an MIM capacitor. To operate the MIM capacitor as a memory device, you first need to form. Once you form the filaments, then you'll see that you're able to do set and reset. So here is the cumulative plot showing the variation in set voltage. So again, and here is the variation for a particular oxide, say hafnium aluminum oxide. So again, you see here that as you change the switching cycles in the device, the current is dropping. Resistance current is dropping. So this is the variation in the device that you need to be aware of and that you need to factor in when you're designing the circuit. So again, just where we are today, we normally use bilayer stacks. We don't use single layer stacks, and bilayer stacks allow us to have a bidirectionality in the breakdown. So that way, what happens is we are able to get weight updates in both directions. So here's again an example using hafnium oxide and aluminum oxide. So how do you model the RF, right? So again, these models are available on Verilog and Spice, and these have been used essentially for all the circuit design that we've done later. So this model is developed in Stanford by Sir Philip Wong. And what is, so the variable, the gap size, so if you think about the filament, right? Let's look at the filament. There's an electrode here, an electrode here. This is the conductive filament, right? And this is the gap. Right? So if you think about current between these two electrodes, the current between these two electrodes is going to be determined by this gap. Right? The current can happen either through tunneling current, trap assisted, Frankel spool, whatever you have, right? By changing the gap, you are able to change the resistance of the device. Right? And so essentially, the control variable, when you're modeling the device, we use G as a control variable, and we want to see how does this G change as you apply a voltage. Nominally, G is set to around 3 nanometers, right? And the G is probabilistic. So how is this filament being formed? Filament is being formed because once I apply an electric field across these two electrodes, oxygen vacancies tend to move and create this channel. So this channel essentially is an oxygen vacancy channel that is created on the oxide. And so you see that as the field here increases, more oxygen vacancies begin to pile up here. Now that creation of oxygen vacancies is an energy-driven process. So you use an Arrhenius barrier to model that process. So the way we model it is the rate of change of the gap is related to this energy required for the oxygen vacancy, and it's also related to the voltage of the applied voltage. So the higher the voltage, the faster the gap closes. The length of the material, right? So that tells you how much gap space is remaining, and the temperature, obviously, this is all degree driven. We also talk about what is known as a G-min. So remember, in the ideal scenario, if this filament reached the top, what would happen? These two electrodes would get shorted, right? And you have infinite current flowing through. So we normally don't use it because the current is not limited. Current is limited by some circuit beyond this. So we use a current compliance normally. So we talk about a G-min and a G-max. So we say what is the minimum gap at which current compliance is reached. So the model is valid only between G-max and that minimum gap. And you see that this model also includes stochasticity, and it is modeled using a noise model added to the G. It also has a temperature model built in, and the temperature basically, as you increase the temperature of the device, the kinetic energy of the ions increases, and so it's easier to form the filament. So you end up, so that is also factored into the model. And Joule heating. So remember, this is a filament, and because of the fact that this is a conductive filament, has a very high current density. So because of high current density, it's going to have a lot of Joule heating here, and that's going to affect the local temperature here, and that's going to change the vacancy creation, etc. here. So that is also factored into the model, right? And the way we model the current, so once you get the gap, the current is simply modeled as an exponential to the gap and the voltage, right? And here, basically the fact is we don't really know what is the current. Can be either trap assisted, can be full cycle, polymonide, or direct tunneling. And we know that all the tunneling mechanisms are exponentially related to the gap and are exponentially related to the voltage. So hence using fitting parameters, so once you get surrogate data, you use fitting parameters to essentially create this model. Right. And so this is a sample RM architecture, right, that is being done and shown here. Again, you see here different voltages, currents here, and the RMAP present. So this is simple for the RMAP. And you're essentially able to create these cross-bar memories using just simple RMAPs. Again, a very good article for those interested in reading more about these circuits. And so if you think about the architecture of a chip, typically consists of multiple cores, right? So because you have to deal with multiple neurons, every core is going to process, consists of an RM crossbar, read circuits, and neurons. Right? And then you essentially have an NOC, a network on chip, to essentially guide the signals through this entire multi-core architecture. So that's how this architecture is based on. You have a spike source which is giving you input signals, and the outputs coming out in spikes, which are then going to be coded up into data. Do we stop here? So we'll stop here, take a break, and we'll be back.
Okay, always will stand for photograph, right? Then we have to.